from 1 to infinity. That is the second solution. y2 of x. So through the Frobenius method, we have established the two solutions. Now, observe that initially I consider my y1 to be Pn of x, later I cancel it out. Why? Because the definition of Legendre polynomial must take care of the constant a0 and a1. Must take care of those two arbitrary constants a0 and a1. There must be a certain value for this. How do we select the values for a0 and a1? We shall see very soon, if not today's class, in our subsequent class, how that generalization will come to be, and we now equate it to the usual notation for the polynomials Pn and Qn. Having said that, from the two results we obtained, let's take some discussion. Let's discuss. Remark that 1, it can be shown that 1, our even coefficient can be written as minus 1 raised power k gamma function of n divided by 2 plus 1 gamma function of n divided by 2 plus k plus half all divided by gamma function of n plus 1 divided by 2 gamma function of n over 2 minus k plus 1 2k factorial, then we have 2 raised power 2k a naught. Also, we can establish the fact that the odd coefficient is minus 1 raised power k gamma function of n plus 1 divided by 2 gamma function of n plus n over 2 plus k plus 1 2 raised power 2k plus 1 all divided by 2 gamma function of n over 2 plus 1 gamma function of n over 2 minus k plus half, then 2k plus 1 factorial a1. These two results can be established. I will leave them as exercise. STV, student to verify this. STV, my listener to verify that. Having said that, let's now make some discussion. Discussion on the two results generated so far. Number 1. Suppose in equation 1, the Legendre equation, n is even. Let me write that equation. 1 minus x squared y prime prime plus minus 2xy prime plus n into n plus 1 y equals to 0. Suppose n here is even, then what happened? Is an even integer, comma, then from the recurrence relation, comma, we are going to obtain the whole of this one as 0. a2k plus 2 equals to a sub 2k plus 4 equals, then everything becomes 0. Full stop. So, if this one becomes 0, then what is the implication? Hence, comma, the solution y1 of x reduces to polynomial of degree n. Polynomial of degree 2k, that is y1 of x involves only even powers. We shall see all this very soon. In a similar form, which I will not bother to write, suppose, so that is 2. So you can write that. Suppose in equation 1, n is odd integer. Then we are saying that the polynomial y2 is going to reduce to polynomial of degree 2k plus 1. And that means that y2 will only involve the odd powers of x. Involves only even powers of x. So those are the two basic discussions. And another thing we need to know, I'll make that one number 3 under our discussion. Number 3, that since y1 and y2 are linearly independent solutions of equation 1, then y1 and y2 are individually solution of equation 1. What does it mean? It means that if you substitute y1 into 1 minus s squared y prime prime minus 2x y prime plus n into n plus 1y, you must obtain 0. It's a must. That the final answer must become 0. That is, put s squared y1 prime prime minus 2x y1 prime plus n into n plus 1 y1 equals to 0. The solution we obtain initially, substitute that equation into this expression, the left hand side of this expression, the final answer must automatically become 0. This can be verified. Similarly, same apply for y2, since the two equations are linearly independent. Now, having done all this, and we have established the fact that some coefficient will automatically become 0 in the long run. So that means that the final power, the series in question is no longer an infinite series. It's going to be a finite series in the long run. So how do we now establish the finite series as far as the Legendre polynomial is concerned? Let's now go back a bit. Let's go back a bit. Let's go back a bit. Let's go back to this. Now, let us write the polynomial in descending order. Let me write it this way. We now write the polynomial in descending order. Descending order. How do we write that? Let's go back to our recurrence relation. Let us go back to our recurrence relation, which is equation alpha. Make AR subject of formula. Subject of formula in equation alpha. Then what do we have? We are going to have AR equals R plus 1, R plus 2, all divided by R minus N, divided by R plus N plus 1, AR plus 2. In this case, our R is less than or equals to N minus 2. Now, substitute. R equals to N minus 2, N minus 4, N minus 6. So that we obtain the following. A N minus 2 equals minus N into N minus 1 divided by twice 2N minus 1 AN. The next one will be substitute N minus 4 into this expression. We are going to have AN minus 4 equals N minus 4 here will give us N minus 3 into N minus 2 divided by, put N minus 4 here, N cancel N, then I'm left with minus 4 multiply by bracket, put N minus 4 at this point for R. We are going to have 2N minus 3, and that's going to be N minus 2. There's a value for N minus 2 already. This is the value. Substitute the value here for N minus 0. The negative cancel out. So we're now left with N minus 1, N minus 2, N minus 3, all divided by 2 multiplied by 4 multiplied by 2N minus 1, 2N minus 3 AN. In a similar manner, let me obtain one more term before we go to the generalization. Now, so following the same pattern, AN minus 6 becomes N n minus 1, n minus 2, n minus 3, n minus 4, n minus 5, all divided by, so this is going to be negative, minus, all divided by 2, 4, 6, multiplied by 2n minus 1, 2n minus 3, and 2n minus 5, an. Let's now go back to our polynomial and see how it's going to look like. So the trial solution, don't forget that we are still working with c equals to 0. So when c equals to 0, in equation 3, we have, what do we have? We have in descending order of power of x, that y will equals to an x to the power n plus an minus 2 x to the power n minus 2 plus an minus 4 x to the power n minus 4 plus it continues. Let us make the necessary substitution. We have y equals the value of an is arbitrary, so we retain this plus an minus 2 has a value, and that value is given as minus n into n minus 1 divided by 2 into 2n minus 1 x raised to the power n minus 2 plus the value of an x raised to the power n minus 2 plus the value of an minus 4 is given as n minus 1, n minus 2, n minus 3, all divided by 2 multiplied by 4 multiplied by 2n minus 1 multiplied by 2n minus 3 an x to the power n minus 4 minus, it continues that way. So let us factor out an into x raised to the power n minus n into n minus 1 divided by 2 into 2n minus 1 x raised to the power n minus 2 plus n into n minus 1 n minus 2 n minus 3 divided by 2 multiplied by 4 into 2n minus 1 into 2n minus 3 x raised to the power n minus 4 minus, it continues. And that is what we have as our solution for y1 of x, the first solution. Now you must know that it is customary to pick a value for our an, like I told you earlier on. Let's pick that value. If an is taken as 1 multiplied by 3 multiplied by 5 up to 2n minus 1 all divided by n factorial, comma, the solution of equation 1 the solution of equation 1 denoted Pn of x, which is the Legendre polynomial Let's call this one equation equation beta. Polynomial of first kind is given by, if this is the solution of equation 1 denoted by this, which is Legendre polynomial of first kind, is given by Pn of x equals, we now go to equation beta. So equals 1 multiplied by 3 multiplied by 5 up to 2n minus 1 divided by n factorial into x raised to power n minus n into n minus 1 divided by 2 into 2n minus 1 x raised to power n minus 2 plus n into n minus 1, n minus 2, n minus 3 divided by 2 for 2n minus 1, 2n minus 3, x power n minus 4 minus dot dot dot, and that is the general form of the Legendre polynomial of first kind. Now, what is the motive behind the selection of an equals 1 times 3 times 5 times up to 2n minus 1 divided by n factorial? Let's make that as a remark. Let's make that as a remark. The choice of an is made so that Pn of 1 will always be 1. We shall establish this one in one of our subsequent classes, how Pn of 1 becomes 1. But this value is selected in such a way that the Legendre polynomial will satisfy this relation. And that is where we are going to draw the curtain of today's class. So far, we have been looking at Legendre equation. In today's class, we have established the solutions of Legendre polynomial, that is, the solution of Legendre equation, which are Legendre polynomials of first kind and second kind using Froben's method. And we have been able to arrive at the general form or the general structure or general outlook of the Legendre polynomial of first kind. How does Legendre polynomial of second kind looks like? That will be in one of our subsequent classes. In the next class, we shall continue on Legendre polynomial of first kind. What are those things that we need to know as far as Legendre polynomial of first kind is concerned? How do we generate those polynomials using the established equations that we have on the board? What are those things that are peculiar to Legendre polynomial of first kind? That will be in our next class and some other subsequent classes as far as Legendre polynomial is concerned. Till that time, have a blessed time ahead.